We are now going to discuss a little bit about what heat is. So first, heat is energy. Nice and simple. And we figured that out previously by realizing that if we just think about work and thermal energy, there's a piece missing. So something that's actually really helpful to think about here is doing a simple experiment where we take a big container of water, we put it over a flame. We know that the temperature is going to increase. An experiment that you possibly haven't done and that you might not expect is if we put paddle into the water and spin it, the temperature will increase. Now, think through the physics of this. We're doing work because if we think about the displacement of each of these little fan blades through the water, we are somehow actually causing a force to push through the water. But this is kind of like a dissipative force, right? That all of that resistance is due to drag, so that's like doing a force against friction. And so we know that that energy is going into thermal energy. It's not going into the water changing its potential energy or suddenly running off to the side. So from a physics point of view, we would expect that spinning a paddle in water, literally moving the water around, would increase its temperature due to the increase in thermal energy, due to simply conservation of energy, dissipative energy in this case. Now, you can do this experiment. If you're careful enough with your insulation, you have an accurate enough thermometer, you wait long enough, you will actually see the temperature of the water increase. So the point is that we can increase the thermal energy in the water either by just adding heat to it, as you might expect, or by literally doing work on it. So at that point, once you've seen that the thermal energy has increased, which would be reflected in an increase in temperature, we say that, hey, we've increased the energy of our water. At that point, we wouldn't really know whether that came from moving the water around, doing work on it, or by adding heat. So heat is one way to add energy through a thermal interaction. We need to be careful about the signs of heat, and this is very analogous to the signs of work. Positive heat, Q is greater than 0, is adding heat from the environment to our system. That's going to happen anytime that our system is in thermal contact with the environment and the environment is at a higher temperature. Heat is then added from our environment to the system. And one important thing to note here, I do occasionally make a mistake on this, is we never say delta Q. It's just a transfer of heat. It's not a change in heat. We're changing the thermal energy and we're changing the temperature, but heat is just added. Now, the opposite is obviously true, that if the temperature of our system is higher than the environment, heat is transferred from the system to the environment. And we call this negative heat. Remember, just like work, we're always talking about the system. So positive heat is adding heat to the system, negative heat is taking away heat from the system. Now, thermal equilibrium is the condition where the temperature of the system is the same as the environment that it's in when they're in thermal contact. And in this case, Q is 0. There is no heat exchanged. So those are the three possible situations. And again, you would just use the temperature difference as long as the system isn't perfectly isolated from the environment to determine the sign of Q. So let's now compare work and heat, since there's many analogies here, but it's really important to understand where they're different. So first of all, work is fundamentally mechanical, heat is fundamentally thermal. They both are ways of adding energy or taking energy away from our system, and again, either adding that energy based on the environment. So if you're adding or taking away energy from the system, it had to come from or go to somewhere, and that's always going to be the environment. So mechanical energy versus thermal energy. Now, for the case of work, we always talked about some sort of displacement and some sort of force, and this would be an external force. Otherwise, you could usually use potential energy. In the case of heat, we're always talking about a temperature difference. We haven't actually talked about how to calculate this yet, but if there is no temperature difference between your system and in your environment, there is no heat transfer. Similarly, if you didn't have a force, or the displacement was 0, like pushing against a wall, no work is done. So the process that we're thinking about that's actually occurring are these macroscopic pushes and pulls, and here we're actually thinking about microscopic collisions. And part of this will actually appear in chapter 20, thinking a little bit more about how all of these macroscopic state variables actually correspond to what's happening on a microscopic level. So then we think about the signs and what equilibrium means. Now, we're not going to talk specifically about work in general for any sort of situation like a ball on a ramp, but we're going to think specifically about our ideal gases, so for instance, as an example system. So a positive value is when we're compressing our gas. Energy is transferred in. For heat, Q is greater than 0, Q is positive, energy is also transferred in, the sign agrees in that case, but this happens when the environment is higher temperature than the system. Now the opposite is true, that work is negative when energy is transferred out through a gas expanding. Q is negative also when energy is transferred out, but this is when the system is at a higher temperature, and you can think of this as putting your system in contact with ice, for instance. Equilibrium is when there's no net force or torque on it, though we don't typically talk about torques for gas canisters, luckily. And equilibrium for thermal equilibrium is when it's at the same temperature. So lastly, I want to distinguish between three quantities that are somewhat similar. Thermal energy, heat, and temperature. These are not equivalent, and the definitions matter a little bit, and here I'm not giving the exact definition, but really trying to summarize it. Thermal energy is a property of a system. So you can't talk about thermal energy in general, and you can't talk about the transfer of thermal energy. When you have a system, you can define its thermal energy. And typically we talk about delta thermal energy because we're talking about a change. And part of this is because we haven't defined it exactly yet. So whenever you're talking about thermal energy, this is the energy of a system and it can change. It's a state variable. Heat, which is Q, is transferred between the system and the environment, or possibly two systems when we talk about calorimetry. It is not a state value. It's not a property of the system. It's energy that is being transferred between systems and environment. Lastly is temperature. This is a state variable and it is related to thermal energy. We haven't talked about how it's calculated yet. You can think about it as being thermal energy per molecule or per atom in a way. So make sure that you recognize we use different variables to represent each of these. Again, E sub TH or delta E sub TH is our thermal energy that we've been talking about for a few chapters now, even just the change in thermal energy due to a dissipative force. Same thing here. Heat is always going to be Q. If you're trying to use H for heat, you're going to be confused and I'm going to be confused. And temperature is going to be capital T. And this is again something we measure in Kelvin in this class. We can talk about delta T because it's a state variable. It can change in a system. So please make sure that you understand the difference between all three of these. And we have been talking about all three of them and we'll continue to talk about all three of them.